It's the second time. Let's dive right into the 8 major semiconductor processes. If you know the process, you can catch the overall flow. Generally, when trying to explain semiconductors first, they can be divided into memory and non-memory depending on the properties of the semiconductor. Here, non-memory products mainly perform calculations such as CPU, GPU, and AP. Alternatively, the process can be broadly divided into design, pre-process, and post-process. This is because the definition of business in the semiconductor ecosystem may also change depending on this. What do you think semiconductors are without? Technology, research, software. There may be no right answer, but we will approach it from the perspective of a practical interviewer, manufacturing. As mentioned last time, the things that semiconductors do are logical, but the process of making them is clearly carried out in the manufacturing process. All semiconductors we know of are made through these 8 processes that I will talk about from now on. Currently, applications have become more diverse and the level of integration has increased, making it more complex, but it is repeated in the current 8 processes. Since only minor parts are added in between, it would be a good idea to memorize the 8 major processes and packaging process during this time. There are 8 major semiconductor processes: wafer, manufacturing, oxidation, photo, etching, deposition, wiring, testing, and packaging. The first 7 processes, from wafer to test, are called the pre-process or foundry, and the packaging process at the end is called the post-process or OSAT. The packaging process includes wafer, die attach, wire bonding, mold, marking, solder ball attach, and packaging. First of all, it would be good to memorize this and be able to explain its meaning line by line. Let's memorize the semiconductor process and packaging process. Drop the beat.
Hey, when will I remember this? Wafer, oxidation, photo, etching, deposition, wiring, test, packaging.
That's not it, buddy. Repeat after me.
외산포식증 배태폐 외다화물폐
외산포식증 배트폐 외다물폐
외산포식증 배태폐 외다화물폐
Wafer, oxidation, photo, etching, deposition, wiring, test, packaging.
외산포식증 배태폐 외다화물폐
외산포식증 배트폐 외다물폐 커먼
외산포식증 배태폐 외다화물폐
This is semiconductor 8. Major packaging. Now let me explain them one by one. First, wafer manufacturing. When silicon is purified and melted, an ingot, which is a huge lump of glass, is created. It is similar in shape to a missile made of a cylinder in the middle. If you cut this thinly one by one, it becomes a round glass plate, and then you make a circuit board by arranging it horizontally and vertically. It gets its name from wafer or waffle, which is a thin round baked bread. The cut wafer is polished, cleaned, and inspected. Second, oxidation. Creates an oxide film on the wafer surface. The reason is to increase the reliability of the wafer, preventing leakage current and incorrect etch. Third, photo. To create a circuit through which electrons pass. It is a process of applying photoresist to react well to light, and then exposing the mask pattern with light. The parts that do not receive light due to the chemical reaction are removed in the fourth etching process. Since the size of electrons is very small, and the circuit board is very fine, the oxidation method is used using a mask rather than a carving knife or laser, and 1/5 of the small mask is burned as if burning an object by focusing on a small part with a magnifying glass. Or even more fine circuit boards are created. There are 2 types of etching: wet etching, which involves removal through a solution, and dry etching using plasma. Due to the disadvantage of wet etching not being able to cut squarely, it has been converted to dry etching for fine processes of 5 m or less. For reference, the photo process is one of the core technologies of the foundry process, and in processes below 7 nanometers, it currently relies on the technology of a single company, ASML in the Netherlands. Because it has an impact on semiconductor production around the world, it has a significant level of influence, including regulations on equipment sales in the United States and designation as a route for the President of Korea to visit. Fifth, deposition and ion implantation process. This is a process where ions are implanted so that a semiconductor has electrical properties and a metal thin film is created to distinguish and protect circuits. Since pure intrinsic semiconductors in the existing silicon state have low electrical conductivity, they provide a starting point for current by providing free electrons or holes through doping with impurities such as arsenic or gallium. Sixth, the wiring process. This is the process of connecting metal wires to transmit electrical signals to the ion-doped ion layer roots. Aluminum or copper are generally used, and because fine lines must be laid, a thin metal film is formed by deposition using boiling or electric shock. Seventh, the testing process. We conduct a testing process to select defective chips, prevent unnecessary manufacturing costs, and monitor any abnormalities in the process so far. There is a DCAC function test for each function, which checks the voltage level, consistency of in-out results, signal timing, etc. And lastly, eighth, is the packaging process. This is the post-process, also called OSAT, and from here, the story behind the completed wafer begins. This is a process where the chip is separated from the wafer, attached to the substrate. Wires are attached to both sides to connect it to the substrate, molded in black, covered with a box, and shipped. On the surface, it appears to be only one process like the previous 7 processes, but since the volume is enormous, we will cover the main packaging process next time. Until now, most of the semiconductor industry has focused on microprocessing, but now that we have reached the limit of microprocessing, the proportion of packaging processes that stack chips and consider efficiency is increasing. Thanks.